Hello. All right. Hello, everyone. Today, our first speaker is Max Liu. Max received his Bachelor's of Science degree in Electrical Engineering from Missouri University of Science and Technology in 2011. He earned his Master's degree in Electrical Engineering from the University of Illinois Urbana-Champaign in 2013, and he continues to pursue his PhD. His research interests cover the areas of optimization-based controls for power distribution networks and smart grid technology, including volt per VAR and microgrid studies. Thank you, Max.
Thank you. Good. Okay, good afternoon, everyone. My name is Max, and today my topic is called the frequency control in microgrids in the distributed implementation and the intrusion detection, basically kind of like cybersecurity stuff. This work is collaborated with Stephen. He's coming from National Tsinghua University in Taiwan, and our advisor is Professor Hao Zhu. So to begin, I give you an outline. So my talk will first I give you motivation and context, and I'll go to show you the inverter-based power sharing idea. Then further, I will go into the distributed droop control based on dual ascent method, which is optimization technique. And I will introduce you my attack models and its countermeasure. Finally, I'll show you some numerical result with a real-time simulator. And finally, I will conclude my talk and answer any question you might have. Okay, Okay, good. So microgrids. The notion of microgrid, maybe some of you not familiar. So basically, you can look at this picture. The dashed line there basically separated what you call the bulk grid, which is a transmission system, to the microgrid. The microgrid basically is a single entity that you can operate by itself, and you have your generation, you have your renewable, and you have its own control algorithm. So even though if you don't take power from utility, you can still maintain its frequency, its voltage, and by the NC standard, everyone should still receive electricity. The microgrid can operate in two different modes. The first one is grid connected. So basically, you see that the switch there, you close it, you basically connect to the utility, and you can provide any type of service the utility require. And also you can operate in isolated mode, which is called islanded mode, which is I mentioned earlier. You disconnect from the utility, however, you're going to continue to supply electricity. So the focus, okay. Oh, I don't know what happened. Okay, the focus of this talk is we're going to develop a control design for inverter interface DER, which is distributed energy resource, on the isolated inertia-less microgrid, which is meaning there's no inertia, there's no rotor mass. Everything is inverter-based. So different type of control algorithm you can implement in microgrid. You can either do a centralized framework or you can do distributed. Now, we picked the distributed control framework for this, this control algorithm is really because it has better scalability and a lower cost. The reason is if you can think about centralized manner, if you need every DER require communication to a centralized computer. However, if you implement the control algorithm distributedly, every DER just need to talk to its neighbor. So you basically cut the communication cost and you just need to talk to the neighbor. So it's the distance is much shorter. And also, distributed control on the frequency regulation is a key for the isolated microgrid. The reason is threefold. First, we have a scarce generation resource. In the isolated microgrid, your primary resource can be the gas generator or it can be the diesel. Those are, that is not a larger unit compared to your big synchronous generator you would have in the transmission system. Second, you have low physical inertia. Like I said, that you don't have a large generator, the rotor mass is not there. So basically, you do not have a lot of inertia in the system to damp out any disturbance. Lastly, is intermittent renewable energy resource. Like I said earlier, you cannot predict how much wind or how much solar you can have, or maybe the fluctuation is quite high. So this is very challenged to maintain a good frequency in microgrid. Also, we want to introduce vulnerability to malicious attack. In this case, is a node attack and link attack I will show you later to our control algorithm. So the goal is we want to develop a robust distributed secondary control with intrusion identification and mitigation abilities. Now, the word secondary here, you can just think is a PI control. The primary is a droop control. So if you have a frequency disturbance, the primary will basically stabilize the system. Now, because it's just a proportional control, you on a steady state, you will have some error, right? So in order to correct the error, you need a secondary control, which is a PI control. You add an integrator to bring the mismatch back to zero. So that's basically the idea behind this work. Okay. So to start with the inverter modeling, everyone should be familiar with the swing equation of the generator. So if you can just look at this, you have a mechanical power input, which is steam input to the generator, and you have some friction, and you have some rotor speed, which is omega m. The output is your P electrical. So this is basically the swing equation, but the first order. I ignore since there's no inertia, so I ignore the second order. Now, if you can do a one-to-one mapping to the inverter base, now the mechanical power output becomes the inverter rating. The friction D becomes the droop coefficient, so depending on your droop curve. And then your rotor speed becomes your frequency. And finally, the output is still the same. So basically, you can treat it like a black box. If I just look outside the inverter, I do not know it's either it's inverter or it's a generator, synchronized generator. So we are trying to mimicking the behavior of the synchronized generator. So now this is a droop curve I mentioned earlier. So different units have different droop curve. And then by the star, basically the unit, the rating. So if you are producing P1 and P2, you look up the curve, and basically you will share the same frequency. Now, our goal is to do the secondary control, basically shift this curve horizontally. So if I shift this, if you see the red mark here, by shifting this curve to here, now actually we can change the frequency of the system. So basically, without this little PI, this is your droop control. Adding this PI by shifting the curve is your secondary, okay? So I'm going to have to give some assumption. The first assumption is this same value DI over PI star for everywhere. This basically saying that the droop curve is designed proportionally depending on your inverter rating. So a larger rating should have a less steep one, and the less rating should have a steeper droop curve. So eventually your proportional droop rates uniform throughout the system. Now, second thing everyone using the microgrid community is synchronized frequency, the center of mass frequency. So basically, this is synchronized frequency is guaranteed under mild condition, and this is basically saying the sum of the frequency divided by its weight, and you can just massage the early equation to be this. This synchronized frequency is guaranteed for every single one of the omega, although the transient state might be not the same, but when they achieve the steady state, which is the synchronization is achieved, they all should share this center of mass frequency. And this is the key for this work, and I will show you why. Okay, let's go. Okay, so our goal is first, we want to have a zero frequency deviation. We want to have the omega c equal to 0. Second, we want to have a power sharing, which means that the power output divided by its rating should be same. So larger unit and small unit, they should output the same proportion. To achieve this, if you look at this optimization, by massage that the droop equation, basically omega c equal to 0 is ensuring if this equation equal to 0. By power sharing, you can rewrite this equal to this. Now, since earlier I mentioned that by design, this is the same everywhere. So by make sure that little pi over di, this part is the same everywhere, you will achieve the same power sharing. So I formulate this in optimization way. So here you can see that the P star is the rating here, and this P is power output, and this P is the shift of the horizontal line, and weighted by D inverse because everyone is divided by Di. And the power sharing is by the subjective 2, by equality constraint. Every Pi over Di is the same because if Pi Di over the same, the larger the power sharing would be the same everywhere because we design the droop rate to be uniform in the system. Now, if you look at this quadratic formula, if you are familiar with optimization, you probably say, hey, Max, you can solve it in one step. If you have all the information centrally, you can solve this because it's a quadratic formula. However, notice in the entire work from beginning till now, I did not mention the network power flow. I didn't show you the power flow model. Therefore, this P and this P is actually coupled. Now, so therefore, there's no way to solve this centralized or even one step. So we propose a distributed way to do iteratively. Hopefully, that we measure the power output from the inverter as a feedback control, so to account for the network dynamics. So therefore, to make your life easier, I just simplify the notation to be C and X. The C basically associated with the power output measurement from your inverter, and the X is basically the shifting factor horizontally. And it's just basically then you can formulate the earlier formulation just become consensus network becomes Ci minus Xi. You want to make sure this is 0, and all the Xi equal to Xj. And that's basically you achieve this optimization. The same as this one. Okay, so how to solve this? I'm not going to go into the optimization form. No, this is not the focus of this. Basically, you introduce a Lagrangian function, and you do a dual ascent updates, and you do all the nitty-gritty trick, and you come up with the x update and mu update. So this one is basically by giving a dual variable, you minimize it. You take the derivative set to 0, and this is closed form solution. And this one basically saying if these two are not the same, you penalize it. So that's basically the idea behind it. As a remark, this here, mu ji equals to minus mu ij, it's because, if you look at this term, by opposite, they should be negative to each other. So in this way, by doing this, I do not have to communicate the dual variable. The only thing I need to communicate is xik plus 1. I will show you the network diagram soon. But also look at our count frequency. So this is our primal variable updates. So if you bring this Ci over the other side and multiply Di on both sides and a summation over the entire network, this will equal to 0 because of the way we design our dual variable. So this is just, you can go into the detail, but if you just believe my word that because this is a Laplacian, if you sum it, it should give you 0. And this is also translate to the count frequency will equal to 0. So basically what the work is after the first iteration, your count frequency, which is the center mass frequency, will be 0. And what the iteration is doing is basically just make sure you achieve accurate power sharing. So this is just a picture just to show you if you don't want to worry about optimization. It's just original is here. You do the first optimization. You shift this pi to here. So now the curve shift. The curve shift, and therefore that your omega will change. So basically, this is just the optimization is doing. So like I promised earlier, you get the primal variable from your neighbor. You perform your dual variable update. So basically, if they have difference between the neighbor, you change your dual variable. And then by obtain a new dual variable, let's see, you do the x update. And after this update, you send this update to your neighbor. So only thing you need to communicate is your primal variable. And our design by doing this is a closed loop control design by incorporating both neighboring node information, which is your xj, and local feedback dynamic, which is your measurement, your inverter power output. By doing this, you can accurately achieve zero frequency deviation and accurate power sharing. And the stability condition, which means you have to pick the correct epsilon right here. And the stability condition actually is publishing on that paper. If you are interested, you can go in there, take a look. So now talk about the more interesting stuff. Let's see if this moves. Okay, so attack model. So now, earlier I mentioned the only thing is transmitting is the primal variable x. So now I want to introduce two kinds of attack models. First one is the link attack. So what is the link attack? Basically, if node j, if this link is being attacked, you just introduce a signal, Lij, mention that you added addition signal from j to I. That's a link attack. The node attack, basically here, saying that if j is being attacked, whatever j is sent out, it has a constant uj. So there's two different types of attack. One is link, just attack the link. And one is node, basically affect all the neighbors. Now, under the link attack, I don't want to go into mathematics, but I just want to give you the result. By just attack the link, you can see that the frequency will not converge, and it's not going to be 0. The reason is you keep injecting only one link to the system. So this is not going to get distributed. So this is going to affect the entire convergence. You're just going to destroy the convergence. However, if you do a coordinating attack, basically, if this is Lij, you introduce a minus Lji here. Since the entire network is kind of a consensus, in this way, the coordinating attack, you basically will achieve zero frequency. Okay. However, that you will not achieve power sharing. The consensus will not be achieved. So although the frequency is 0, that your power sharing will be destroyed. In this way, it will be insufficient power sharing, and you might violate your constraint of your inverter. But also look at this mu ij. This is our indicator function, basically saying that if something is being attacked, since all in the end, everything should be consensus. So by an attack neighbor should be much greater than the good neighbor, so mu ij. So this is one of the signals we're going to use later to detect the attack. Now, if you look at the node attack, basically just sending the information to all your neighbors. In this case, that omega c is not equal to 0, but it will be converged. If you're coordinating attack, if you just send the opposite of what since it's distributed algorithm, you're going to propagate the entire system. Basically, you will see no effect at all. Now, in the end, in this case, the consensus still can be achieved, but in one way, you're still going to have a voltage frequency mismatch. The other one, you're just not going to see anything. And so in this case, same thing, the dual variable will give you some information. So basically, this dual variable is played a key part of comparing the good node and the bad nodes. Okay, so this is our countermeasure. So you basically use the dual variable as an indicator function. So if the dual variable is if this is greater than 0, something happened. Then you look, it changed. If it doesn't change, it's a node attack. If it's changed because it's not converged, then you're going to get a link attack. So basically, that's the detection algorithm. And then if you have a link attack, basically disable the link. If you have node attack, you disable the nodes. And if your graph is no longer complete, then you need to reconfigure it. So okay, so let me just show you the numerical result. This is actually done in the real-time digital simulator, OPA-RT. So by changing the disturbance load change and t equals 10, you can see that after the first update, the omega c go back to 0. And you can see all the others, omega is not the same, but eventually they achieve the same omega constant, center mass frequency. And in the end, we achieve accurate power sharing. So this is a small network. So now if you go into the larger network of I believe is how many bus? Is a 14 bus network. And then we have 6 different DIC. And here we have a link attack. So link is going from 4 to 1. So if I plug this, you can see detection. The purple one is actually much higher because we receive the attack from 4. And in this case, you can see the frequency is not going to converge and the power sharing is being destroyed. That's the first case. However, if you do a coordinating attack, so basically injecting the opposite negative of this signal, now your frequency is converged, but your power sharing is not accurate. However, in order to detect this, you can see from DIC1 and DIC2, you can see this is coming from node 1, DIC1, and in this case, it's coming from DIC2 because that's our signal, 2 and 1. And then the third case is basic. Let me see. The third case is a node attack. Node 4 is being attacked, and here you can see the omega c is not 0, but it's converged, and the same accurate power sharing is being achieved, but this is not the frequency is not at 377. Okay, so in this case you can see the attack frequency 1.4 because it's coming from 1. And if you do a smarter one, which is a coordinating attack, in this case you attack both 6 and 4 in opposite signal, but in the end you do not see any effect. The omega is at 60 hertz and power sharing is being accurate. However, in order to detect this, you look at their dual variable. You can see it's coming from 1, and this one is coming from 6. So our conclusion is we have designed a frequency control using a dual ascent method. Second, we are designing malicious agent detection by just looking at neighboring information, and also be able to identify potential malicious node or link in the system. And we report a flag to the centralized computer, and they can decide which node and which link is being attacked. Our future work will be, okay, I cannot go to my future work. Okay, it's considered time-varying system operating condition. Right now, we just introduce, assuming that the load is not changing in this window. So we want to investigating what happens in a dynamic situation. Also, we want to include voltage control because right now we're just doing frequency. So we want to add voltage to it. And finally, we want to study more complicated attack scenario and potential unidentified ones. So that's my talk, and I believe that's my reference. Any question? Thank you. Yeah, Professor.
Yeah, I'm struggling with an implementation question. Certainly in a conventional grid with the synchronous machines, all of the time rates of change in frequency are defined by the time rates of change in fluxes and physical shaft speed and all the other physical parameters in the machine. In an inverter, typically there's a local oscillator, a phase lock loop, and something else actually generating the frequency signal, my ability to even measure the frequency is kind of cycle. So if I want millihertz accuracy, it's going to take 1,000 cycles to get that level of information out of the system. So how do you seem to sort of have assumed that you know the frequency and you can kind of plug it in instantaneously.
Okay, it's a good question. So let me go to, if I have the extra, let's see if I go to my backup slide. Go. It's not working. So basically the question is, how do you measure the frequencies? It's much faster than the conventional transmission grid, right? The thing is this here, we are actually not measuring the frequency. The omega here is actually the control signal we send into the inverter. So this is what conventional called the grid supporting mode of the inverter control. So if I can go to my inverter diagram. Okay, here. So basically, eventually my droop control is happening here. The goal is to get is theta I. This theta I is a control signal. We are not measuring. The only thing we are measuring is from the terminal bus. Is basically we are measuring the P and Q. And this P and Q serve as the input to the controller, and output is the angle. And this angle is go into the DQ transform. So we actually are setting the frequency of that inverter. So we are not measuring the frequency. It's different.
Which means there's a phase lock loop.
Yeah, that's a phase lock. That's a phase lock loop right here. Yes. So, but we are not measuring the frequency. We are setting the frequency as a control signal to this inverter design. This is a little bit different than the traditional, I guess, the governor. Yes.
In the attack detection part, we are saying that you see that the process will not converge. So you're saying that you wait for multiple until it, like, I mean, how can you tell it's convergent?
Well, right now,
by only comparing the local Q variable.
How do I know it's convergent or not convergent?
Yeah, you are waiting for like a long time until it.
So you're talking about this one, right?
Yeah.
Okay. So we have a detection window of 10 seconds. So you can design the detection window however long you want. But we are assuming that within this 10 seconds, the load is not changing. You can make the detection window much smaller if you have a system much faster. But it's all depending on your window. So in this window, we can see this not zero. Then we can know something is wrong. And what is wrong, then we basically look at if it's increasing or also it's very easy to see. But as an attacker, I probably not want to do this scenario because it's very easy to be detected. If I'm smarter, I will go into a coordinating attack because then my frequency is fine, but my power sharing is violated. So I just show you this is a very naive example because if I'm an attacker, I would not do this because as soon as I do this, every agent will look, hey, my frequency start dropping, something is wrong. If my low is not changing, something is wrong. But if I'm a smart attacker, I will go to the coordinating one. Frequency stay the same, however, my power sharing is violated. But in this is more interesting case, right? And in this case, you can still be able to see the different depending on your time window. Does that answer your question?
So is that a time window?
Yeah, I mean, we assume that time window to be not the low is not changing. Any more questions? Good, thank you. Your turn.
All right, our next speaker is Yue. And Yue is a PhD student with Professor Krein, and his research interests are numerous and include subareas of microgrids, grid-tied renewable energy, energy storage, motor drives, energy-efficient buildings, transportation electrification, and electric thermal integrated systems. Thank you, Yue.
Thank you. So all those areas are power electronics based. So, but there's a lot of collaborations for sure in the ongoing work in power systems and thermal dynamics and so on. This is a PDF format. Just either all right, and this works great. Okay, so the topic today is 20 times real-time modeling and simulation of more electric aircraft, thermally integrated electric power systems. The part of this presentation was presented back in early November last month in France at the conference. It's a transportation electrification conference. Our collaborators are from electrical and mechanical. Mechanical have Professor Ali and his student Matthew Williams, and the rest are electrical, including 2 of my undergraduate research assistants. So just the high-level backgrounds of some trends here. So the electric power in aircraft is increasing dramatically over the past few decades. So if you look at the even 777 is pretty big. It consumes 230 kVA. But the Boeing 787, which is smaller than 777, but still consumes 1,000 kVA. The reason is majority is because of the removal of bleed air systems. Traditionally, the environmental control systems and a lot of mechanical systems are powered by the bleed air. Bleed air is part of the engine airstream, and now it gets rid of that because of the inefficiency. Instead, there are multiple generators tied directly with the engine shaft and generate electricity to power the environmental control system and other. I will cover that a little more. So it's getting more challenging to model, especially coupled, multi-domain, multi-physics domain coupled system, electrical and thermal. At the component level, which monitors the temperature behaviors of the component or detection hotspot, and also at the system level, which to model the air temperature change inside the cabin, fuel temperature and pressure, and valve pressure, all that. So our goal here is to develop multi-physical domain model, incorporate just to model all the things I just talked about in both electrical and mechanical domains. So this work has been a few years of effort with Rolls-Royce. It started back in 2012 when a few other Professor Krein students worked on it. I will acknowledge them later. So the goal here is to first develop a library of all the components in electrical, thermal, hydraulic, and make it more module and plug and play sort of environment in Simulink. And we do not use any Simulink library built-in models because we don't know what's behind them. So we start from scratch. And once we have the library models worked out, we start to build subsystems in electrical, thermal, and so on. So the tool set objectives, as I mentioned before, you want to be modular, multi-physics domains, dynamic, meaning there's a time-scale separation, both transient and steady-state behavior, and scalable, meaning smaller system or larger system. Performance want to be faster than real time, just on a standalone computer, standard computer, and user interface with a very user-friendly I/O layout. So the talk today is more about more electric aircraft, such as the Boeing 787, and in the future there is a full electric aircraft, meaning the entire powertrain is also electric. So that means just the power system on the aircraft itself we can view that as a microgrid system or standalone power system. So a lot of challenges behind is to how to stabilize that power system, how to utilize the generator power more efficiently, and so on. So there are many future directions we can head into. As I mentioned before, the major difference between the 777 and the 787 is the non-bleed architecture. So yeah, just very quickly about the system architecture differences. 737 or 777, there are only 2 generators, small generators, and back auxiliary power unit. And 787 has 6 in total, engine-tied generators, and the power level is 10 times 737. And also you notice the distribution bus is more spread out versus in 737. There are only main buses at the front of the aircraft. So some of the main differences between 737 and 787 is the increased voltage level. It's more for the voltage, for the power density and efficiency purposes. So in 787 there is a 230 volt bus versus 115 volt in the 737, and this is the engine tied, so it's a variable frequency bus. And also there is the introduced 270 volt DC bus versus no such voltage bus in the 737. The 270 volt is mostly as like a DC link in the motor drive, is to power the large power units such as environmental control systems. So following this architecture, we modify the previous 737 model into a new architecture. So just have an overview of the system. We have the generators, and this is like a nominal power rating to 230 volt AC bus, and some goes to 115 volt AC bus, and some are to the 270 volt AC bus to auto transformer rectifier unit. This is the efficiency conversion of the conversion, and the 28 volt bus for the electronics loads. And here it shows the power distribution. So our goal here is to, as mentioned before, is to model them in components, but coupled with thermal and run fast, and so on. So here's some high-level methodology approach, how we can achieve those goals. For the generators and the rest of the AC power system, we use a DQO synchronous reference frame to speed up the simulation speed without losing the transient information. And for the power electronics, we use average switching modeling for power electronics converters for power losses like information, but without knowing the detailed switching modeling. And each component is tied with thermal predictive model to monitor the temperature and so on, which I will cover later. So in the next few slides, I'll just give some high-level ideas of the modeling approaches of the individual components. The first one is the generator, electrical. It is modeled as the one-field synchronous machine. These are some standard machine models you found in Professor Sauer's book, but they are modeled in DQO reference frame. The thing we added is the temperature dependent resistance model K here, and power loss is also standard equation. And this power loss is fed into thermal equation. This is the first order lumped thermal capacitance model to represent the temperature. The challenge here is to identify the heat transfer coefficient, and with the help from the mechanical folks, they are calculated by the Nusselt number and thermal conductivity of the fluid. For coolant, we have some other, there's called Jelinski correlation. It was not my work here, but just to tell you how we link the things together. And exciter is to provide a DC field to the main generator, which requires a DC field, and the DC field of the exciter is powered by the battery. So you see here, so it's modeled as a one field generator, similar to the previous, but there's a smaller scale. And the diagram here just show the power and control signals. So here's the high level of the converter, including rectifier, inverter, and rectifier modeling techniques. Is the we mainly use the average switching power losses to model the conduction loss and the switching loss, and we do not need information about switching, but we as long as we know the switching frequency and rise fall time of the semiconductor devices and the voltage and current. These are, I think, can be found from Professor Krein's textbook, or a variation of that. Okay. Again, the power loss is coupled with the thermal model, and it's similar to before. There's a lumped thermal model, and the challenge is to identify the heat transfer coefficient and I forgot this, the S opt, but it's also related to Rayleigh number, the system. And the battery model, we do have a dedicated battery system. So in order to also meet the timescale requirement, we have a multi-timescale parametric battery model in second, minute, and hour scales to predict the dynamic behaviors within these scales. So the model precision of this is in the millisecond time range, and this model is able to predict the dynamics in that scale. So I mentioned it's a parametric model because we have to extract the parameters from lab test, including the RC constants based on the state of charge variation. So for more information, I have a paper on this, or talk to me. Again, this is coupled with the thermal system. It's another first order lumped thermal capacitance model, and will predict the instantaneous temperature of the battery. The transformer and the electric loads are relatively simple in our model. It's just a standard equation. And loads, we have user-enabled real power and reactive power input. And we always assume it's a balanced three-phase system. So here are some of the Simulink blocks to show the scales of the model. We have, I just covered the electrical system, but there are a lot more in the mechanical environmental control system and the flight operating system, and also hydraulics, including the hydraulics, the fuel and other pressure information, and the engine models, which is the input power into the electrical. And under the electrical system, we have more blocks, just to show, as I covered before, we have the load, generator, AC buses, power electron converters, AC-DC load, DC buses, and battery. And going one level lower, we have the library that models each component with the necessary input and output information in generation, conversion, and storage. In summary, we have 79 component models, almost 4,500 total blocks, and it's a multi-physics domain model here. So we run some simulation study to test what the model can provide us. So we created this 5-hour mission run. It has the altitude information, also the engine thrust information, and that links to the load requirement of the electrical system, as well as many other thermal and hydraulic systems. And we find literature that has some breakdown power into various mission segments, the power usage. We use this power requirement as the like a standard as the input of the model requirement. So we customize some of the loads here at the different buses, 115 volt AC, 230 volt AC, 270 volt DC, 28 volt DC, and we also assume generators 1 and 2 covers the top 2 loads, and the generator 3 and 4 covers the DC loads. This is all hypothetical. In reality, I think they are all mixed up, but it's just to test the simulation speed and get some results on the voltage and temperature waveforms. So we run 1,000 Monte Carlo simulation runs with a maximum 10% random weights. So for isolating the electrical power systems, the simulation speed is about almost 50 times real time. And in the coupled electrical and thermal engine systems, the simulation speed is about 22 times real time. And here are some of the waveforms you guys may be interested in. For example, this thing is the 270 volt DC bus. This is the entire mission, and here's some of the zoomed in information. Like this is the startup, and there's also a transient, but this is more detailed. And this one is the 230 volt AC bus information, is similar. And the temperature of the generator, for example, we can predict the temperature changes and identify if there's any, if our cooling is sufficient, for example. So in addition to all these voltage and current, power, temperature, pressure, all that information. We want to put this model into use somewhat. For example, in my PhD dissertation, I used this model to study some of the thermal storage-based solution to mitigate the power variation in the aircraft loads. In addition to the model, I proposed some control on using the virtual synchronous machine concept, like to mimic the inertia of the power system using thermal storage. And this is the high-level power electronics and control diagrams, and here's some of the control algorithm using that. And for the mechanical folks, he is interested in future work such as hierarchical control in the mechanical loads and so on at the multiple timescales. So in conclusion, in this talk, we presented the background information about aircraft, more electric aircraft, and the challenges regarding the power dynamics information usable by the engineers to predict power flow, thermodynamics, and a few other necessary pieces of information. So in our work in the past few years, we developed a comprehensive electrical power system model and thermal for more electric aircraft or standard aircraft. As I mentioned before, it has necessary details for future R&D at the company, and our model results in 20 times fast simulation speed. Acknowledgement thanks to the Rolls-Royce Corporation and past collaborators. A lot of the model blocks are built by the past people. Turku, Shrikant, Chris, all Professor Craig's students, and also Craig, Professor Jacoby, and they're also from other departments. So, thank you. And we are looking to, well, we're willing that you guys collaborate with us and take advantage of the model for future, for example, the machine design work and also the inverter design work. But this is more like the system level, like behavior over a mission profile. But definitely we can add more details if we need it to, and so.
Why do you think they kept an AC bus on the 787?
What about?
Why did they keep an AC bus, a regulated AC bus on the 787, not the generator side?
Oh, 115 volt? You mean the regulate 400 hertz? I think that's just for normal AC electronics. That's not changed yet into the DC domain. I think I think it's a similar question, like why not doing DC microgrid versus AC microgrid. I think it's a similar question, but I do think if everything is converted to DC, then we can reduce the power electronics conversion losses and all that between the adapters and all that.
Well, there's still other reasons, right?
So other reasons.
Fault management is still an art in aerospace. It's not. The fault finding is on the ground, and that also tends to limit where they're willing to put DC in an aircraft.
Okay, thank you. And personally, I look forward to working more in the power system dynamics in the more electric aircraft for future research, such as the stability issues and storage issues, and like the reactive power compensation and power quality issues. Like especially it's going to tens of maybe hundreds of megawatts power level. The power electronics is important, but also the system stability and all that are also becoming more important. So it's another direction I'm heading to. Okay.
Another round of applause.